Hmm. How I can see the chat box here? Ask questions. But then otherwise this is not. Okay, understood. What will be the Mhm. Okay. Actually, good, correct. Yes, dear Akshay, the topic is same. The schedule that we will follow as same that we sent you in a Excel sheet. Okay, the topic that will be same. Now today the topic that will be linear regression that I will discuss. Okay, so start the session. Okay, now is my voice audible to you? Okay, fine. So now our today's topic, the linear regression. So always I prefer the chalk and board so that I will not use uh, the PPT. Okay, in this 10 days FTP program. So first of all, I welcome you all in this 10 days FTP program, E&ICT, that is organized under the aegis of E&ICT Academy. So the topic is linear regression. So in this linear regression, that today that we will cover under this one, first one is the simple linear regression. Second, that is a multiple linear regression and polynomial linear regression. And if time permits, then we will discuss also the regularization. The need of regularization, why we use this regularization, that we will discuss. So today that we have 4 hours, okay. So in the morning 10 to 12 and the second half, in the second session that we are having the time of 2 to 4. So let's see how much that we can cover this linear regression part. So first, that is a simple linear regression. Before start this topic, this linear regression. So first, let us understand this regression. So regression, there is a this very common term, this regression and classification. So first, let us understand the two this terminology, regression and classification. So regression means, in a very simple way, if we just uh, uh, an example. So if, let's say, output is in the form of continuous value, okay, if output that is in the form of the continuous form means the output that may be 7.2, 5.6, 3.9 is something, some numeric value. Okay, if output is in the continuous form, then that is a regression. That is a one way of difference between the regression and classification. So there are other difference is also there, that the regression and classification. So first difference is, if the output is in the continuous form, okay, if the value that is in the continuous form 7.2 or 1.2 or 1.6, so that is a kind of the regression problem. While in case of the classification, again, that we classify this classification in a two part. First, that is a binary classification and multi-class classification. Multi-class classification. So binary classification, the output that will be yes or no, means only two class. Okay, means either the patient is suffering from a disease or not. Means the if the output is in the form of yes or no, means two class, that is, let's say this one is a class 1 and let's say this one is a class 2. So only the two classes we are having in the output, that we call as a binary classification. Okay, it is coming this classification under this category of classification. It's a binary classification. Now next one is the multi-class classification. Multi-class classification, if we are having the more than two output, okay, more than two output. Maybe let's say the output, suppose in the form of, let's say, 1, 2, 3, 4. Okay, means in classification, output is in the discrete form, not in continuous form, in discrete form. Here this is the discrete form, here it's a discrete form. Okay, if in the discrete form, if only two class, that we call as a binary classification. Okay, if in the discrete form, if more than two class, that we call as a multi-class classification. So there is a one difference between the regression and classification. So let me again repeat, the this continuous form, and here that is a discrete form. So binary classification and multi-class classification. Correct. This word that is a linear, it suggests the data set is a sort of linear. Okay, means that is an assumption. This one, that is an assumption. Assumption is the data set that must be linear. Then only we can apply this linear regression. Okay, that we will discuss in more detail. Uh, just now, for the time being, just you understand the meaning of this linear. Linear means this data set. Okay, is sort of linear. If suppose data set is non-linear, then the linear regression that will not give the better result. So this is a linear regression. Correct. Now come to this simple linear regression. So in simple linear regression, here input and output. So single input and single output. Okay. So if, let's say, if we have one input feature, if one input feature and one output, then it is coming under this category of the simple linear regression. If we have more than one input, maybe two, maybe three, maybe four, so input feature, so input feature, let's say two input feature, three input feature, means more than one input feature. then that is a multilinear regression. Okay, so more than, let me write here, more than one input and single output and single output. Okay, now this polynomial linear regression, here the assumption is, in this case simple linear regression, the assumption is the data that must be a linear. In multiple linear regression, again the same assumption, that is data set that again that is a sort of linear. But here is the polynomial linear regression. So if suppose if we are having the non-linear kind of data, okay, so non-linear kind of data, then we can apply this polynomial linear regression. Then the polynomial linear regression. So now you can ask one question here. So polynomial linear regression. So why means the question is, you can ask one question here. This polynomial linear regression that we apply on the non-linear data set, then why it is called as a linear regression, polynomial linear regression? Okay, this linear word means that is the data set that should be the linear. Then that polynomial linear regression, as I said, we can apply this polynomial linear regression if we are having the non-linear data set. Then why it is called the polynomial linear regression? It should call as a polynomial non-linear regression. Yes or no? So that we will discuss in detail at the time of this polynomial linear regression part. Okay, and here the multiple input for sure means more than one input. Here also more than one input and single output. Okay, and this one regularization. So regularization that we will discuss in more detail. Regularization, but for the time being, just you understand here this regularization that we will use to overcome the overfitting. Okay, to overcome the effect of overfitting. So overfitting, underfitting, bias variance trade-off, that we have separate session for this uh, overfitting and underfitting. So that we will discuss in more detail. So to overcome the problem of this overfitting, the effect of overfitting, we use the regularization. Okay, and for this regularization, two kind of regularization is there. One is the lasso regularization, and another one that is a ridge regularization. Correct. So this is the overall picture of this linear regression. So now come to this first simple linear regression. So simple linear regression. Now let me see, is there any doubt or question in the chat box? Okay. Okay. So no question in the chat box. So now come to the simple linear regression. So simple linear regression, first we will understand the mathematics of this simple linear regression. Mathematical this formulation. Okay. So as I said here, simple linear regression. So single input, the single input and single output. Okay. And output is in the continuous form. continuous form, just you can understand, let's say um, the input is kind of number of years of experience of an employee, number of years of experience, okay, and this one is the input, and output, let's say the salary package in LPA, salary package in LPA, okay. So let's say this one is a X, this one is a Y, correct. So if, let's say, suppose number of years of experience, suppose two years of experience, then salary package, let's say for example, so 5 LPA, okay, um 3, then maybe then 7, then 4, then maybe 15, okay. And that it depends on other factor also, but just for the timing, just you understand this, only that we are having here in this data set only single input and single output, okay. So still you cannot find this kind of data set in a real life problem. Just this is simple linear regression is just for the sake of understanding, because in the real life that you are having the multiple input data, or more than one input, okay, more than one input and single output. So just for the sake of understanding this simple linear regression, this is the first algorithm, this is the first algorithm in machine learning, okay, and it is coming under the supervised machine learning. So this is the first algorithm. So, and this one is a very fundamental algorithm, fundamental algorithm. Okay, fundamental, and this foundation also. So number of years of experience and salary package. So first you have to understand the single input and single output this data set. So this one is a kind of number of years of experience, and this one is the salary package that is in LPA. Okay, so maybe the salary package that is 5.6 or the package that is 10.2. Okay, the kind of that is continuous form, that is output that is in the continuous form. Clear? Also, this number of years of experience that it may be in 2.5 or 3.6 or 4.2, that is years of experience. So this kind of data, if suppose if we are having, and the assumption is that is it should be linear. It should be linear. Okay. So like linear means that is the X, is that is the input, here this Y, that is the output. So data set kind of this one. But obvious more number of years of experience, the salary package that will be more. Okay. So let's say if this kind of data set if we are having, then we need to find the best fit line. That is the best fit line. We have to find the equation of this line, and this line that we will call here, that is a best fit line. Okay, best fit line. So if you give me any unseen input, number of years of experience, this X value, any unseen, okay, means that is a test data. If you give me the test data, let's say X is equal to, let's say 15, then I can easily provide you the output, the salary in package. Okay, that is based on this data set. Clear? Correct? So that is a X, this one is a Y. So for that, I need this Y is because single input and single output. So the equation that will be Y is equal to mx plus n b. Okay, and this is the equation of a line where Y that is the output, Y this is the output, X that is the input. Okay, M this is the slope of a line, and B that is the intercept. That is a B that is the intercept. So this one is the intercept, M that is a slope. In slope, that is a change in y-axis by change in x-axis. That is a slope. Okay. So ultimately, we need to find this M and B value. These are my parameters. These are my parameters. If I if I get to know this M and B, then I can easily provide you the output, that is salary package in LPA. If you give any unseen, if you give me any unknown this input, I can provide you the output, that is salary package in LPA. So for that, we need to have the value of m and b only, correct? So how we can find this value, this m and b, this parameter? So, so now the question is, we need to find the best fit line. Okay, so let's say again I'm drawing this data set here. This one is a kind of data set. Okay. And this is the best fit line. Best fit line means the meaning, the definition of this best fit line means the line that should pass through all the data point. If 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 the line pass through all the data point, that will be my best fit line. Okay, clear? So this cosine, that is this one, is actual salary package in LPA. This is X, this one is a Y. This X, no, sorry, not X, this is the cross, this is a data point, and this data point, this one here, that is a Y. This one is actual salary, correct? And this, that is a, on this line, this give me the prediction, that is a Y cap. My model give me this Y cap, that is Y cap, that is a prediction. Okay, actually the salary package is more, but my model gave me the salary is the person that should have the less salary. Okay, but actual the salary package is more, clear? So this line that should pass through all the data point, actually that cannot be possible, but the that is the ideal case, that is the ideal case. But if the line that it pass close to all the data point, close to all the data point, that will be my best fit line. So how do I know this m and b? Because if I want to draw a line, I should know the value of m and b, correct? So once I know this m and b, then I can easily make a line, and this line, that is my model. That is my model. If you give me any x, let's say this one is a line. If you give me the x, that will be my y. Correct. So that is the overall. That is a kind of interpretation of this linear regression. In fact, it's a simple linear regression. So now you see this y and y cap. So y is the actual output, and y cap, that is a prediction. Okay, y cap is the predicted output, that my model that gave me, that is a predicted output, and y, that is the actual one. Y, that is actual one. So now this distance, this d, that is y minus my y cap. Okay, this distance, or I should say this is the error kind of this e, or this distance, that should be zero, should be zero. Okay, so this is my e, or that is a distance, that is a y minus a y cap. Okay, so if I consider all the data point, so I should write here, that is a yi minus yi cap summation of I is equal to 1 to n. That is my error, this is my error. Okay, and square of this, and square of this. So the question you may ask here, so why this square, this term that has come here, is y minus and y cap, that is the error, that is the distance. Okay, so as per the definition of the best fit line, the line that should pass close to all the data point, ideally it should be equal to 0. This error, this distance, this should be equal to 0. But in place of this y minus and y cap, here I considered I means I, that is a subscript, means that here I considered all the data point. Okay, this y1 cap, here this one is a y2. Okay, this is y2 cap, likewise. So yi minus and yi cap, that is a square of this one, and summation of I is equal to 1 to n. That is the error. Okay. So now the question is, why the square that has come here? Now, if let's say if I do here y minus m y cap, that is a mode of this one, okay, y minus m y cap, and y minus m y cap, that is a square, okay. The difference between these two, y minus m y cap mode of this one and square of this one, I prefer this one, okay, y minus m y cap. The reason is this mode, actually it is not differentiable, is not differentiable, because we will use hereafter the gradient descent, okay. There is a one approach to find the optimal value of the parameter, okay. So the gradient descent means we will do the differentiation. So this one is not differentiable, this mode, that is not differentiable. So that is one reason not to take this mode. So one reason is not differentiable, okay. Why it is not differentiable? Because no, I think this is the the uh, kind of plot of this mode, okay. But where is the square? Just this one is this one, like this. So y is equal to this, and y is equal to this x square. Clear? So y minus and y cap. The second reason is I want to just penalize the outlier. I want to penalize the outlier. Okay. So that is the second reason. So just to have this square term. Okay. Here. So now here this error, or you can say this one is a loss function, or this error function. Both are the same thing. Loss function or this error function. And this error function or loss function is OLS, ordinary least square. This one is ordinary least square. So ordinary least square, that is this one, is the name of the loss function in linear regression. So there are various loss function in the machine learning. Different algorithms are there, different loss function. But here in this linear regression, the loss function that we call as the ordinary least square, that is the OLS. Okay. So now yi minus and yi cap and square of this one. So it should be 0, but not 0. It should be minimum as we can. Okay. So yi minus and yi cap square of this one. So the next is, so this error function, okay, let's say this error, or you can say that is a loss function. Both are the same thing. So yi minus yi cap and square of this one. So where I is equal to 1 to n. Clear? Okay. So now where y is, that is mx plus b. Okay. Y is equal to mx plus b, where y that is output, x that is the input, and m slope, and b that is the intercept. So y cap, that will be mx plus b. Okay. So can I write this y cap is equal to mx plus b? Now here you can ask one more question. So you can ask here, so y is equal to mx plus b, y cap should be mx cap plus b. Yes or no? Because m and b, that is a parameter, x that is the input, y that is the output, and cap means that is a prediction. Okay. The model, my model that give me the value of output, that is a salary in package. Okay. Salary package in LPA. So that is y cap. So it should be mx cap plus b. Okay. So, but here that I have written here, y cap is equal to mx plus b. So the reason is, now you see this. This is the x and this one is a y. Okay. And let's say this one is my actual data, and let's say this one is my line. Okay. So now the point is, this is my y, and this point, that is my y cap. Clear? Now for this data point, my x and x cap both are same. here, that is x, correct, and x cap, that are both are the same thing. But here y and y cap, that are different. Y means that is the actual one, and y cap, that is a model, that is a prediction. Okay, so that's why that I have written here y cap is equal to mx plus b. So can I put here y cap here in this one? So now summation I is equal to 1 to n yi minus में mx minus में b and square of this. This is my error. This is my error. Clear? So now I am writing in advance the value of m and b. Okay, for sure that we will derive the expression of m and b. So b, that is y bar minus में m x bar. Okay, so now we will derive this b and m also. So where m, that will be the summation of y minus में y bar xi minus में x bar, and where I is equal to 1 to n, and summation again xi minus में x bar, that is square, that I is equal to 1 to n. So this is my m, and this one is b. So we have to just derive this m and b both. Okay, so now come to this again equation number, let's say equation number 1. So equation number 1, that is this yi minus yi cap, that it become like this yi minus mx minus b, that is square of this one. So now this error, that should be minimum. Okay, that should be minimum. So how we can find out the minima? So just you do the differentiation of this error function with respect to b. That is a kind of way to find the minima. So now let's say this one is a e. Okay, so now dou e by dou b, that should be equal to 0. Okay, for minima. So where e is this one, so let me write again in a fresh base. So that is e is equal to summation I is equal to 1 to n yi minus में m xi minus में b and square of this one, and dou e by dou b, that should be equal to 0. So uh, I have to just do the differentiation of this one. So differentiation, this summation I is equal to 1 to n minus 2 yi minus में mx minus में b is equal to 0. Correct? So now I is equal to 1 to n yi minus में mx minus में b, that is equal to 0. So now if I open this summation, okay, and if I divide both the side, that is n, that is the number of data point, where that is n, that is the number of data point, and that is the number of data point. Okay, so now summation I is equal to 1 to n yi divided by n minus m summation I to 1, that is x divided by n. Okay, here we considered all the data point, so that is xi, and here that is summation I is equal to 1 to n and b divided by n, that is equal to 0. So this, can I write this y bar? Y bar is the mean. Y bar, this one is the mean. So let's say y1, okay, y1 is 2, let's say y2 is 3, then 4, then the mean of this one is 9 by 3. Okay, that is 3. So this y3 is, that is a y bar. Okay, so let's say this one is a y1, y2 and y3. So y bar, that will be y1 plus my y2 plus my y3 divided by 3. So yi divided by n, and summation of I is equal to 1 to n. So y1 plus y2 plus y3 divided by n means n, that is a number of the data point. Okay, so that is a y bar. Now minus m, this xi summation I1 to n divided by n, that is again that is a x bar. Okay, and minus में this b, but summation that is I is equal to 1 to n, so that is nb divided by n, that is equal to b and equal to 0. So now my b from this equation, b that will be equal to y bar minus m x bar. Okay, now you see this one, that is same for the y bar minus m x bar. Okay, so that is b is equal to y bar minus m x bar. So I can easily calculate the mean of this output and mean of the input. Okay, but I should know the value of m for b. Okay, if I calculate this b without m, that we cannot calculate this b, so I should know the value of m here for b. Okay, so now that is the first, okay, the formula. The second one, that is for m. So again the same way we do the differentiation of this e, but differentiation of e with respect to m, that will give us the value of m. So in the next page, so again I am writing this e. E is I is equal to 1 to n, that is yi minus में m x I minus में b, and square of this one. Okay, uh, so now that is e with respect to, that is m, dou e by dou. So dou e by dou m is equal to 0. So let me just check whether is there any question in the chat box. So now up to so far, if you have any doubt, okay, any question, just you please put up your question in the chat box. Let me just, yes. Mm. So Kaushik Ghosh Chaudhary, by sparing, do we also eliminate the possibility of negative value? Negative value, yes, negative value also we want to just eliminate. But the point is, uh, actually, the mode is not differentiable. Okay, and the second is, uh, because if we do the mode, then the negative value that also we can eliminate. But the question is, the big reason is, we want to penalize the outlier. Outlier means something that is lie or when away means that is very unusual. Okay, means let's say, if suppose number of years of experience is 2 and salary package in LPA that is 50 or 1 CR. Okay, 1 CR. So 1 CR, that is a salary package in LPA, and number of years of experience, that is a 2 year. Okay, so how can it be possible? Maybe. Okay, so that is kind of, that is outlier. So that is the reason. Now second, but what what is x cap and x are not same? X cap and x, that both are same. Okay, x cap, you see, x cap and x. Okay, y and y cap, that is a different. Y, that is the actual salary package in LPA, and y cap, that is a my model that give me the salary package. Okay, according to my model, that is a y cap, and actual one, that is a based on this input output, that is a data set, that is a training data set, I should say, the training data set. So y, that is the actual one. Okay, and for this y, input is x, y cap, again that is x, is x cap, that is it, the same is x. So now next, it's the distance between x and x cap. X and x cap both are the same. X and x cap both are the same thing. Okay, so now I want to minimize the difference between this y and y cap. Y, that is the output, actual output, and y cap, that is the predicted output. Okay, clear? So now you don't have any question further, just you write clear. Otherwise, okay. Now next is the distance between x, how divided by n in third step. Okay. See, now I come to my this. So this n. Okay. See, actually, why I divide by n? Actually, I want this mean value. Okay. I want the formula of this p, because we are having the y1, y2, y3, y4, y5, and so on. Okay. So if I divide uh, this yi, summation of yi by n, so that is a y bar. If I divide this xi, okay, by n, that is the x bar. So now my, at the last, the formula that will become b is equal to y bar minus mx bar, where bar, y bar is the mean of the output, x bar, that is the mean of the input. Clear? So first we should have the value of m, and then thereafter we can easily calculate the value of b. Question is there. How can we suddenly divide by our own? We are taking differentiation. Yes, see, this one differentiation that is finished uh, in this equation, up to this equation. So this is the differentiation. Okay, now differentiation that is equal to 0, that is fine. Okay, this minus 2 that will go to this 0, that is fine. So now I is equal to 1 to n, this one. Now this is the equation. This one is the equation. Okay, and this one summation is yi minus में m xi minus में b is equal to, that is summation of this one, that is equal to 0. Okay, now can I can just divide the whole equation by this n in the both side, left hand side and right hand side. So left hand side, that is divide by n, divide by n, and divide by n, and this divide by n, because this b, that is number of times, this summation, that is n times, so that is nb, and nb divide by n, that is equal to b. Now I hope it will be clear to all of you. So that is y bar minus में m x bar minus में b is equal to 0. Correct. Thank you. Okay. So next. So now come to this m part. Yes. Now differentiation dou e by dou m is equal to 0. Correct. So now I have b is equal to y bar minus में m x bar. So can I put this here, b here? So now my E, that will become I is equal to 1 to n yi minus में m x I minus y bar plus m x bar and square. Now this whole equation, that is in terms of m. Now I can easily do the differentiation of this E with respect to m. So now again, just you do the differentiation, partial differentiation with respect to m, that is equal to 0, because I want the minima of this m. So now just you do this one. The 2 summation I is equal to 1 to n, and this yi minus mxi minus में y bar plus mx bar. Okay, uh, minus xi and plus x bar, that is and equal to 0, that is equal to 0. So correct. So now in the same way, this 2, just that will go to this right hand side 0. Now summation I is equal to 1 to n yi minus में m x I minus में y bar plus में m x bar and this negative sign that is xi minus में x bar that is equal to 0. Clear? And this one I'm writing here, that is summation I is equal to 1 to n yi minus में y bar, okay, minus में m that is xi minus में x bar and xi minus में x bar, let it be as it is, that is equal to 0. Okay, now clear? So now just multiply this xi minus में x bar with this yi minus में y bar minus में m xi minus में x bar. So in the next page, this summation I is equal to 1 to n yi minus में y bar yi minus में y bar and xi minus में x bar xi minus में x bar minus m xi minus में x bar xi minus में x bar and square that is equal to 0. This one. Okay, so now this summation I is equal to 1 yi minus में y bar, now xi minus में x bar, okay, equal to this m, this summation I is equal to 1 to n xi minus में x bar and square, and my m that will be summation of I is equal to 1 to n yi, that already that we have output, correct, minus में y bar, I can easily calculate this y bar, okay, same color yi minus में y bar and xi, that is the input, minus में x bar, that is the mean of this input. Now summation xi minus में x bar and square of this one summation I is equal to 1 to, that is the my m. This is my m. So if I know this m, I can easily calculate the another one, that is b is equal to y bar minus में m x bar. And if I know this b and m, okay, if I know this b and m, then if you give me any unknown value of x, then I can provide you the value of output, that is salary package in LPM. So y is equal to mx plus b. So this is the kind of mathematics behind this simple linear regression. Okay, so now just we will do the hands-on also. Okay, we will do the hands-on also. Okay, so if suppose if we have very small data set, if we consider, let's say 200 data points, or let's say 1000 data points, where this x different number of years of experience that we are having, and according to this, that is output that we have, then how uh, we can just calculate the unknown, this test data, okay, output of the test data. So this one is a kind of simple linear regression. Clear? So now let me take up some more question. Okay. Yes, yes, clear everything. Why we need to find out the b? Okay, b, that is the intercept. B, that is the intercept. Okay, um, intercept, in this intercept, that is a word, that is a term that we use in a sense of line. You can say that is offset also. Offset. Okay, so b, that is a offset. Let me just come to this screen. So let's say this one is my m. This is my, sorry, this is my line. Okay. So that is y is equal to mx plus b. So this is my intercept, that is a b, and this one is a slope. That is slope, that is a change in y-axis by change in x-axis. Okay. So the line, that best fit line, that may be here, that can be this one, this one, this one, anything, this one, this one. Okay. So the point is, I have to find the best fit line so that I can correctly predict the output based on the data set. Okay. If you give me the any unknown value of this x, um, I can correct predict the output if we have the best optimal value of m and b, best optimal value of m and b. So that is a kind of the mathematical formulation of this linear regression. And if you are having any doubt on this one linear regression, then I'm happy to answer all the questions. And if you don't have, then next thing that we can start. The next is, yes, the next that we, there are two things, that is a, one is a closed form solution, closed form solution, and second one is a non-closed form solution. Now, what does it mean? Closed form and non-closed form solution. So let me check, is there any? We have changed the sign in xi minus x. Wait, minus x. Xi minus x. Xi minus x. Okay, the next step is this one. So now xi minus x bar. Okay, just you just take the this negative of negative side minus of this one. Okay, and you can take this minus to the right hand side of this equation. Then this will be y minus and y bar, this xi minus x bar. Now is it clear? Okay, fine. Now come to this closed form solution and non-closed form solution. So now see the difference between this closed form solution and non-closed form solution. So closed form solution, that is, if we have suppose in a concrete formula. Okay, uh, if we have suppose concrete formula, that is, let's say for example, so a x square plus में b x plus में c is equal to 0. It's a kind of quadratic equation, and x value, okay, x value is minus में b plus minus में b square minus में 4ac divided by 2a. Okay, means this one, that is, we have the one formula, mathematical formula, okay, to find this roots of this quadratic equation. Okay, so that is a, this is the closed form solution. This one is a closed form solution. Okay, so closed form solution, if we have in a formula positive, okay, negative, this multiplication or division. Okay, if something, if we have the operator like this one in a formula, that that is a closed form solution. Okay, or that is one concrete one formula, if we have, that is a closed form solution. Non-closed form solution means integration, differentiation, logarithmic, exponential. If we are having kind of in expression, that is this one, that is a non-closed form solution. Correct. So now the point is this ordinary least square. Okay, that is a kind of loss function. Okay, loss function in linear regression. this one gives us the closed form solution where M and B, that is the formula of this B, that is y bar minus may m x bar, where M formula that we are having this one M1. So this one is a closed form solution. Right here, this closed form solution. This one is a closed form solution. Okay, so this is a one way of uh, finding one way of method of finding this optimal value of M and B. Okay, the another method is that is a non-closed form solution, that is gradient descent. Gradient descent is also kind of the method, another way to find out the value of M and B. Gradient descent, through gradient descent also we can find out the value of M and B through this ordinary least square, that is this is the one method that is a closed form solution. This is also we can use to find out the value of M and B. So now you can ask the question, so uh, although this we got the formula of M and B through this ordinary least square, then what is the use of this gradient descent? Okay, already we got the formula this M and B. Okay, and this ordinary least square, that is a very simple and very intuitive, this ordinary least square, and through this ordinary least square we got the formula of M and B. So now the question is, what is the use of this gradient descent? Okay, this one is also the optimal value. This one is also that is a minima or optimal value. Okay, gradient descent also that gives us the optimal value, that is M and B. So now the difference between this ordinary least square and gradient descent, that we will discuss the answer of this question in multiple linear regression. Okay, multiple linear regression. So just you noted down this question. Okay, this there are two approach. One approach is ordinary least square, another approach is gradient descent. Okay, and both the approach to find out the value of optimal value of M and B, correct? Then this gradient descent, is there any speciality of the gradient descent? Okay, is there any drawback in this ordinary least square, or is there any kind of specialty in ordinary least square? So something that we will discuss at the time of multiple linear regression. Okay, so now in this first hour, that now I conclude this first 1 hour, this session, this simple linear regression. Simple linear regression. So let me again this revise the simple linear regression. So simple linear regression, single input, single output. Okay. Multiple linear regression that we will discuss in next 1 hour. Those that is more than one input and single output. Polynomial, that is more than one input, but if we have the data set sort of non-linear, then we can apply this polynomial linear regression. The output that is again single. And regularization, just to overcome the problem of this overfitting, again it is divided into two parts, that is a lasso regularization and ridge regularization. Then next that we had discussed mathematical formulation of the simple linear regression. Actually, ultimate goal is to find out the best fit line, and the best fit line, the definition is the line that should pass through close to all the data point. Then only we can have the optimal value of M and B. And if we have this optimal value of M and B, if you give me any unseen or that is test input, then we can provide easily the output. Okay, so that is a single input, single output. Now this is the kind of understanding of the data set. Okay, so just give me a second. Hello, sorry, actually, and phone. Okay, just so now come to this. Okay, so now this one is clear. Now the error signal is y minus and y cap. This error function, okay, you can call as a loss function. And the loss function in terms of the linear regression that we call as a here ordinary least square, so OLS. So yi minus and yi cap the square of this one, okay. And this yi cap, that is that I have written here mx plus b. So I put here this value of y cap, this mx plus b, okay, because of this negative sign, this minus mx minus b. And if we do the differentiation of this one with respect to b, then we got this formula that is of this intercept b is equal to y bar minus my mx bar. And the second time that we will do the differentiation of this error function, okay, and with respect to m, then we got this formula of this slope, this one, okay. And both the formula of this one, that is a closed form solution, okay. And the non-closed form solution, that is a gradient descent that we will cover in the next session, okay. Maybe not today, maybe any other day. So the next one, okay, up to so far, if you are not having any doubt, then we will start this multiple linear regression. Multiple linear regression. Clear? So let's take a 5 minute break. Okay. So now time is 11:07. So that we will start 11:15. Okay, 11:15 to 12:15. Meantime, if you are having some doubt, some questions based on this linear regression, simple linear regression, then you can ask. Okay. Now next variant under this linear regression is multiple linear regression. So in multiple linear regression, that we may have more than one input, then in that case we can apply the multiple linear regression. Okay, in place of simple linear regression. So that is y is equal to mx plus b. Okay, means that is a single input here. That is a single input, that is only this x. Okay, the single input, and that is single output. Clear? So now um, this one is the kind of the line equation of line. So in a more generalized way, so I can write this equation: y is equal to beta naught plus में beta 1 x1 plus में beta 2 x2. Okay, so where uh, or let's say uh, up to this one, beta naught plus beta 1 x1. Okay, so this is also the equation of a line where this beta naught and beta 1, these are the constant. X1, that is the input, y, that is output. Clear? So y is equal to another way of representation of this line. Y is equal to beta naught plus में beta 1 x1 plus में beta 2 x2. Okay, so this one also, that is uh, uh, in the 3D. Okay, so where this x1 and x2, that is a two input feature, this x1 and x2 two input feature, and that is a y, that is a output one. Okay, this one is a 2D. Y is equal to in this one in 2D. Here in 2D there is a line. It's a 2D, this one line, that is a x and y. Clear? Now here in this, that is 3D, that is the plane. This is a plane, and let's say this one is a data point. Some of the data points lying above this plane, some of the data points are lying below this plane. Okay, so we need to find the this plane, beta naught, beta 1 and beta 2. So beta naught, beta 1 and beta 2. Clear? Now in 4D, y is equal to beta naught plus में beta 1 x1 plus में beta 2 x2 plus beta 3 x3, that is in 4D. Okay, likewise, if we have more number of input, more than one number of input, then we can apply this multiple linear regression. Clear? So now in this uh, example of this multiple linear regression, now I will take this 2D. Okay, because the reason is we can just visualize the 3D easily. Okay, in place of this 4D or more than this 3D. So that is a visualization that is easy. That is the reason to take this y is equal to this equation, y is equal to beta naught plus beta 1 x1 plus beta 2 x2. Okay, and we will generalize also. We will generalize in n dimension case. Okay, what else if we have more than two dimension? What else if we have more than one input? Then that is a multiple linear regression. Clear? So now the equation, that is y is equal to beta naught plus beta 1 x1 plus beta 2 x2. Okay, so and so on. So can I write this equation: y is equal to beta naught plus summation I is equal to 1 to n beta I xi. Okay, so ultimately we have to find this beta I. Okay, beta I. So where I is 0, 1, 2 and so on, and where beta naught, that is the intercept. Okay, that is the intercept. Intercept, this is the term that we use normally in the line of equation, and beta naught, that we call as a offset also, offset, or you can say the intercept. So y is equal to beta naught and this beta I into my xi. Clear? So let's say this one uh, in a more generalized way. So let's say if we have three input, we have three input. Okay. So now in this case, y is equal to y1 is equal to beta naught plus beta 1 x11 plus beta 2 x12 plus beta 3 x13. Okay, y2 three input, okay, and single output, so that is y1 for this one, beta naught plus beta 1 x21 plus beta 2 x22 plus beta 3 x23, and third output beta naught plus beta 1 x31 plus beta 2 x32 plus beta 3 x33. So now let us understand this terminology of this x11, okay, this x11, this x12, x13, this x21, x22, and x23. Likewise, this x31, x32, and x33. So this x11, x1, x2, and x3, and that is y, that is the output. Okay. So let's say this first input feature is let's say the marks in the 10th standard. Okay. X2, that may be the input feature that is marks in the 12th standard, or third, that is x3, that is a marks that is in a CGPA in a BTech. Okay, that is CGPA in a BTech or percentage in a graduation. And y, that is output, that is uh, you can take that output, that is again the same way, that is a uh, salary package in LPA. So y, that is the salary package in LPA, that is output. So here now x11, that is a, let's say this is the first student, okay, or the first kind of this applicant. Okay, so there's a first applicant, this x11, this again that is a x2, that is a 12th marks of first applicant, CGPA of the first applicant. This one is the second data. Okay, this x21, that is x21 is this one x21, x22 is this one, x23 is that is a third input feature of second student, x22 is a second input feature of second student or second applicant, and this one is the first input feature of the second applicant, and there is a third one more applicant. Okay, the x31, so first input feature which is having the 10th, that is a marks in the 10th standard of third applicant, x32, that is a second input feature of third applicant, and x33, that is a third input feature, that is a marks percentage CGPA in graduation of this third applicant. Okay, and this y, that is the output, that is salary package in LPA. Clear? So now x11, x12, x13, x21, I hope this will be clear to all of you. So x11 is a kind of simple nomenclature, okay, that we assign the this input, kind of first input, second input, third input, and this first input, second input, third input, that is, you can say this is a first row, second row, and third row. Clear? So let's say if we have three row and three input feature, then this kind of equation that we can make y1, y2, and y3. Clear? So let's say if we have n data, okay, means n number of row, n number of row. So n number of row. So in that case, y1, okay, y1 is equal to beta naught plus में beta 1 x11, okay, and y2 and up to so on, that is a yn. Okay, so can I write this all this in a matrix form. So this one is a y1 to yn. Okay, let's run this one. And is equal to, this one is beta naught plus beta 1 x21 plus beta 2 x22 plus beta 3 x23. Okay, and likewise this beta naught plus beta 1 x n1 plus beta 2 x n2 plus beta 3 x n3. Clear? So here that is n, that is number of rows, that is n, that is the number of rows or number of data set, number of applicant. Okay, and let's say here 3 input feature. So in place of 3 input feature, let's say m input feature, and n number of rows, number of rows means number of observations, number of observation means number of kind of applicant. Okay, number of applicant, number of rows, number of observation, all are the same. That is n, that is a number of rows. How many number of data that you have, that is a number of row. M, that is a number of input feature, that is a number of input feature. Okay, so in the this example we have only 3 input feature: 10th standard marks, 12th standard marks, and graduation. Okay, so based on these 3, the output, that is salary package in LPA. Okay, this kind of data set if we are having means more than one input. In the previous simple integration we have only the single input. Okay, now here this multiple linear regression is a more than one input, x1, x2, x3, like. Clear? Now let me check the chat box. Okay, fine. Great. So yes. So let's say if m input feature and n number of rows. So how can I make this matrix y1, okay, y2 up to this yn is equal to this beta naught plus beta 1 x11 plus beta 2 x12 and so on plus beta n x1 n. Yeah. Now beta naught plus beta 1 x21 plus beta 2 x22 and so on, beta this n x2 n. Clear? And so on, that is a beta naught plus beta 1 this x n1 plus beta 2 x n2 plus beta n x n m. Okay, so can I write this equation y1 y2 up to yn is equal to this uh, beta naught. Okay, uh, so better to just write uh, the matrix form. One one x11 x12 up to x1n, and here that is a beta naught. Okay, so 1 x21, x22, and so on, that is x2n, and up to this 1. Okay, xn1, xn2, and up to xnm. Here beta 1, beta not beta 1, up to this beta n. Okay, so now here the dimension of this output, that is n cross 1. Okay, and now can you tell me the dimension of this matrix dimension of this one? The n cross m plus 1, and dimension of this one is it should be this beta naught m plus 1, this cross 1. So here this one is n cross m plus 1. Okay, so now beta naught beta 1 up to this, yes, sorry, m, because m, that is input feature. You see this m, that is an input feature. Okay, so that is n input, and m, that is input feature. Here is m input feature. So now here that is m plus 1 cross 1. Okay, and this one, that is n cross m plus 1. Clear? So this output is y, that is a dimension is n cross 1, and this one ultimately, that is y is equal to x into my beta. Y, this y is n cross 1, x is m cross m plus 1, and beta, that is m plus 1 cross 1. Clear? So now can I write this y is equal to x into my beta? Okay, where y is this one, this is my y, this all this thing, this is my y. Okay, x is this one, beta is this one, and y is this one. Y is equal to x beta. Okay, and my y cap, that will be again, that is x into my beta. Okay, as and the dimension of this y is n cross 1, dimension of this one is n cross m plus 1, and dimension of this one is m plus 1 cross 1. Clear? So now can I put this y cap is equal to x beta here? So now error, my error function, that is y minus में x beta transpose into में y minus में x beta. Clear? So now actually in multiple linear regression, our goal is to find out this beta I. Yes or no? Our goal is to find out this beta I, optimal value of beta I. Clear? So beta I, that is beta naught, beta 1, beta 2 and beta 3 and so on. So if we have this beta I, then if you give me any unknown this text value, okay, test data point of this x, I can easily provide the output y. That is the objective. Objective is just to find this beta I. Clear? Yes or no? So up to so far, if you are having any doubt, then please you ask. Otherwise, let me check